Energy methods. We are going to derive few expressions like strain energy stored due to axial loading, strain energy stored due to bending, strain energy stored due to torsion, and how to use these expressions to determine the slope and deflection of a given structure when it is subjected to an external loading. You're going to see this. What is strain energy? For example, whenever an external load is acting on a structure or a member or a body, the body undergoes deformation or the straining effect. The energy absorbed during this straining effect, we call it as strain energy. We call it as strain energy. Let us see now the strain energy stored due to axial loading. Let us take a member whose one end is fixed at the top and the other end is free, having length L, the cross-sectional area A, Young's modulus E. And the work done, external work done, is given by average load into displacement. And this external work done should be equal to the internal work done. That internal work done is nothing but the strain energy stored, which is represented by capital letter U here. Okay, so for equilibrium, internal work done should be equal to the external work done. Okay, so internal work done is nothing but capital letter U for equilibrium. So U is equal to average load into displacement. Okay, so average load 0 plus W divided by 2 into delta L is equal to half into W into L. From solid mechanics, delta L is equal to WL by AE. Just substitute this delta L here, you get this expression, and multiply and divide by A, you get this W square into AL divided by 2A square E. Area into length is nothing but a volume, and W by A, load by area, is nothing but a stress, sigma square into AL divided by 2E. And strain energy stored per unit volume is equal to sigma square by 2E, so which is the formula for uh, strain energy stored due to axial loading. Now strain energy stored due to axial loading, you can write like this also, W square L by 2AE also. Next, strain energy stored due to bending. Strain energy stored due to bending. Let us consider a simply supported beam subjected to UDL W. For example, from solid mechanics, M by I is equal to sigma by Y is equal to E by R. From the sigma is equal to M by I into Y. So we know this expression, strain is stored per unit volume, sigma square by 2E. Just substitute the sigma here, M square Y square by 2E I square. So now let dA be the elemental area and dx be the length. So dA into dx is nothing but the volume. Okay, I've taken this volume to the right hand side numerator, and this y square dA, I can take it as I, the area moment of inertia. So m square I dx divided by 2 ei square, I will get cancelled. So integration m square dx divided by 2 ei is the strain energy stored due to bending. Now strain is due to torsion. Consider a solid circular shaft subjected to torque T, which gives the angle of twist theta. So strain energy stored to U is equal to half into T into theta. So from solid mechanics, T by J is equal to C theta by L is equal to tau by R. And for a solid circular shaft, the torque transmitted is given by T is equal to tau into pi dq by 16. So U is equal to half into, substitute this T here and theta here. So theta is nothing but tau L by CR, where C is nothing but modulus of rigidity. In some books, it is taken as G, capital letter G. Okay. And let us introduce R is nothing but diameter by 2, D by 2. So DD will get cancelled here again. And tau into tau square. So pi D square by 16 into L by C. So I need like tau square L separately and pi by 4 D square as area. So tau square pi D square by 4 into 4 I have taken separately, L by C. So pi by 4 D square area into length becomes the volume. So tau square by 4C into volume is nothing but strain energy stored due to torsion. Let us apply the strain energy stored due to bending expression, how to get the deflection for the given simply supported beam subjected to a point to W at the middle. So we know the support reactions and the beam, the given beam is symmetry, and the support reactions will be like W by 2 here, W by 2 here. And how to write down the equation, for example, if we try to write the equation For this, u is equal to integration m squared dx. So if I take a section something like this, okay, something like this, and at a distance x, for example, at a distance x, something like this, okay, x, okay. So if I write down the moment equation about this, w by 2 into x, w by 2 into x is the moment, okay, and strain is stored by half of the beam will be same of the other half, so I can multiply by 2 and I can integrate between the limits 0 to L by 2, so m squared dx by 2 ei, so is equal to w square integrated, apply the limits, you will get w square L cube by 96 ei. Okay, so which is equal to the external work done of this off into W into delta, off into W into delta. So delta, so equate this external work done, this internal work done. So WW will get cancelled and 2 will get cancelled with this, 2 you get 48. So delta is equal to WL cube by 48 EI is the formula. That is a central deflection for a simply supported beam subjected to a point load W at the middle. Now eccentric point load, simply supported beam subjected to an eccentric point load, that is the point load is applied at a distance of A from left hand and at a distance of B from the right hand. Let us try to determine the deflection under the point of application of the load, and this support reaction is WB by L and this support reaction is WB by L. Okay. So now let us write the moment equation between for the limit 0 to A and 0 to B. We know this is WB by L. Okay, take a section, and if this is my X, for example, this is my X. Okay, write down the moment equation about this WB by L into X. You can see here, and if I take a section here, and if this is my X and this is my x WA by L into x, WA by L into x. So m squared dx divided by 2a, m squared dx divided by 2ai. And if you just integrate and apply the limits, you get this expression. And after simplification, a plus b is nothing but L. It will get cancelled here. So you get the strain and stored due to bending for an eccentric point load on a simply supported beam, W square, A square, B square divided by 6 EIL. And this is equal to the externally applied, external work done of into W to delta equated. So delta is equal to WA square B square by 3EIL is a formula for a simply supported beam subjected to an eccentric point load. Now cantilever beam subjected to a point load at the free end. Let us find out that tip deflection due to W at the tip, delta. So again, U is equal to m squared dx divided by 2ei. So consider a section like this at a distance x, write down the moment equation W into x. Okay, so right side clockwise negative. Anyway, we are going to square it, no problem. And the limit is 0 to L, m squared dx divided by 2ei. So w squared x squared dx divided by 2ei. And if you integrate x cubed by 3, apply the limits L cubed by 3. So w squared L cubed by 6ei is the strain and is stored for a cantilever beam subjected to a point load at the tip. And this is equal to the external work done of into W to delta. If you equate it, delta is equal to WL cubed by 3 EI is the formula to determine the deflection at the tip of a cantilever beam subjected to point load at the tip or the free end. Now let us take a problem where we have the cross section, that is I value is different. Okay, for first off you have I and the other off you have 2I. Okay, the cross section is not uniform. Okay, the cross section is not uniform, that is geometry is not uniform along the length of the beam. So U is equal to m squared dx by EI, and we know this is 60 load is acting, kilonewton is at point load acting at the middle. So 30 30 either side the support reactions, and for the first off the limit is 0 to 4, and if I take a section here and if this is my x means 30 into x the whole square to dx into 2ei, limit is 0 to 4, and here in this case again limit is 0 to 4 and 30 into x, if I take a section here 30 into x the whole square dx into 2ei, I is nothing but 2i, I is nothing but 2i. So if you just simplify this after integration applying the limits, you get 14,400 by ei is the strain and is stored for the given beam for the given loading, and external work done is nothing but off into W into delta here, W is 16, so delta is equal to 480 by EI, which is the deflection at the center of the beam, center of the beam. And if you go to the next case, here uh, you can see here also A, B, C, and BC is having I, and AB is having 2I, and we are trying to find out the vertical deflection at C due to 1 kilonewton acting at the tip, or the free end X modulus is given, and I value is also given, m squared dx divided by 2ei. And if I take this as a section, and this is my X, for example, let me draw and show you. And with respect to this, and this is my X, that is strain energy stored would be equal to strain energy stored in BC plus strain energy stored in AB or BA, whatever it is. And if this is my X, for example, if I try to write out the or take the moment, write the moment equation for BC 1 into X, for example. This is nothing but here limit is 0 to 3, okay, 0 to 3. And for this BA or AB, limit is 0 to 4. With respect to BA or AB, 1 into 3 is the moment, okay, 1 into 3. So 3 squared dx divided by 2e, I is nothing but 2i. So after integrating and apply the limits, you get 13.5 divided by EI, and the external load is nothing but, I mean, external work done is nothing but off into W delta. W is 1 kilonewton. So delta is equal to, after substituting all these values here, okay, everything is in kilonewton and meter, and E should be in kilonewton per meter square, and I should be in meter per 4. Hence, the delta is equal to 0.0045 meter. That is the vertical deflection at C. Now, Castiglione's first theorem, what it states that in a linearly elastic structure, partial derivative of the total strain energy with respect to load is equal to the deflection of the point where the load is acting, the deflection being measured in the direction of the load. Let us see how this Castiglione's theorem is applied in the problem. So now let us check, for example, it says that partial derivative of the total strain energy, that is dou u by the load. If P is the load acting at a point where the deflection is required to be calculated, dou u by dou P. Now, for example, you look at this problem. Yeah, this is the strain energy stored here, dou u by dou W. If I differentiate partially with respect to W, I get the deflection at a point where the W is applied. Dou U by dou W, I get WLQ by 48 EI. So, and similarly here, this is the strain and stored. Dou U by dou W, I'll get this expression. And here also, this is the strain and stored. Dou U by dou W, I'll get this expression. And here also same here, dou U by dou W of this, you'll get this expression. Similarly here also, this is strain and stored. Dou U by, here it is 1, right? So it is given in number. So you can do that also by keeping this in terms of P or whatever it is, you can get this answer. And coming to this, now the simply supported beam subject to the UDL throughout having length L, how to find the deflection at the center of the beam. Now here in this at the center, no load is acting. So what we have to do is some simplification we have to do. Now let me introduce an imaginary point load of Q, point load which is acting at the middle. So the area, the support reaction here will be WL plus Q divided by 2. Here also WL plus Q divided by 2. So if I take a section, for example, if I take a section and write down the moment equation, for example, okay, the strain energy stored for this and for this will be same. So you can integrate between the limit 0 to L by 2 and you can multiply by 2. So WL plus Q by 2 is the reaction here into X, okay, into X here it is given, okay, into X. And this W dual is acting, gives counterclockwise, so minus W into X by 2 is the moment arm, so Wx squared by 2, this is the moment, the whole square into dx divided by 2EI, divided by 2EI. So 2 to this 2 and this 2 gets cancelled, you get this term. And the delta, how to obtain this delta? As per the Castiglione's theorem 1, partial derivative of the load which is applied at a point where the deflection is required to be calculated. So dou u by dou q, dou u by dou q. So this power you just differentiated partially. So 2 times into delta is equal to dou u by dou q. So differentiate the power, WL plus q divided by 2 into x minus Wx squared by 2 into partial derivative of q, that is q with x by 2 you will get. So if you differentiate partially q means you will get x by 2. So into dx by ei. Now q is nothing but as it's an imaginary load. Put q is equal to 0. Put q is equal to 0 here in this expression. You will get this. Now you integrate and apply the limits. You get 5 WL power 4 divided by 384 EI is the central deflection for a simply supported beam subjected to a UDL. Now let us take a cantilever beam which is subjected to a UDL, and it is required to calculate the tip deflection. Same way, let us find out the, write down the moment equation for this by considering this as a section, and this is my X. Okay, so Q into X, right? Q into X, the moment, and this W into X into X by 2, that is WX square by 2. So both are right side clockwise, both are coming out to be negative. Anyway, we're going to square it, it will be plus, it will be plus. So now this is the moment m squared dx over 2ei. So now you just differentiate partially with respect to q. Dou u by dou q is equal to delta. Limit is 0 to L. Okay, 0 to L. So differentiate partially this 2 into this bracket term, and partially differentiating q, you get x term. Okay, now take this. Put q is equal to 0 in this. Okay, put q is equal to 0 in this. Now you integrate and apply the limits. WL power 4 divided by 8 EI is the tip deflection, that's at the free end of a cantilever beam subjected to an UDL. Let us take this type of problem for this. Okay, it's a quadrant circle kind of thing. There's a quadrant arc. One end is fixed, and the other end the load P is applied vertically downward, and it is required to find out the vertical deflection at B as of now. And this is U is equal to m square dx divided by 2ei. E is equal to m square dx divided by 2ei. Now let us consider, for example, this is R. Okay, and if I consider a section like this, and if this is my theta, for example, if I try to take a moment with respect to this, so this will be, if I take a moment with respect to this distance will be r sine theta. So PR sine theta will be m. Okay, PR sine theta will be m. Dx is nothing but, if I consider a small region, something like this, and if this is in some books, if you see here, the formula m square ds, it will be given. Suppose if this is my ds, and if this is my d theta, for example, so this arc length is nothing but r into d theta. Okay, r into d theta. Okay, so this is r sine theta. So p into, if I take moment with respect to this, p into r sine theta is the moment square into r d theta divided by 2 ei, and limit is 0 to pi by 2, and sine square theta can be written as 1 minus cos 2 theta divided by 2. Once if you integrate and apply the limits pi by 2, you get this expression, and you can equate this to the external origin of p into delta bv, and by cancelling that, delta bv deflection, vertical deflection at b is nothing but pi pr cubed y divided by 4 ei, or else with the help of Castiglioni's dou u by dou p, if you just differentiate partially this equation, you will get this deflection. Okay, now if I want to find out the horizontal deflection at B means, so we have to introduce an imaginary point load at B, that is Q, acting right hand side. For example, your wish, you can put it in the left hand side also. Okay, so if you get positive value, means our assumed direction is correct. Our assumed direction is correct. Now, as I told you already, I'm taking a section something like this, taking moment with respect to this, and this is theta. Okay, I'm taking moment with respect to this, and this is nothing but PR sine theta. This distance is r sine theta. Now for Q, this is my distance. Okay, total is r, and this distance is r cos theta. So r minus r cos theta will be this distance. Okay, that is r into 1 minus cos theta. You can see here Q into r into 1 minus cos theta. So this is the total moment. So m square dx or ds, whatever it is, arc length r into d theta divided by 2 ei. Now partially differentiate with respect to q, dou u by dou q. So after differentiation, partially r into 1 minus cos theta will get one term extra because we are doing differentiating partially. So you get this term, and put q is equal to 0. After putting q is equal to 0 here, so this is a reduced expression. Then you integrate it. Okay, integrate sine theta cos theta is nothing but sine 2 theta divided by 2. So integration of sine theta is minus cos theta. Integration of minus sine 2 theta is nothing but plus cos 2 theta, because sine 2 theta is, if it is integrated, you will get negative. Okay, so after applying the limits, the upper limit and lower limit 0 to pi by 2, and this is the horizontal deflection PR cube by 2 ei. That is, our assumed direction is correct. Our assumed direction is correct. Now let us determine this, find the vertical deflection at E when P is applied, and X modulus is 200 GPa, and the cross-sectional area for all inclined members is 1000 mm square, and for horizontal members it is 800 mm square. Okay, so this reaction, support reactions, as the structure is symmetric and the load is acting along the line of symmetric, RA will be RA is equal to RB is equal to P by 2. Okay, you can take the moment also. You can write the moment equation. MA is equal to 0, 4 into P. Okay, 8 into RB. You can find like this also. RA is equal to RB is equal to 0.5 P also. And take the free body diagram of this. This is RB is acting. The unknown reaction is taken as assumed as a tension. Okay, these are the forces acting here. Resolve it vertically. I get FBD to be minus 0.577 P, and resolve it horizontally. You get this horizontally. If you resolve means left hand side negative, right hand side positive. Resolving vertically, the sign convention is upward is positive, downward is negative. You get this. FB is tension and FBD is compression. Just immediately you just mark it in the figure. Tension away from the joint, and positive negative means towards the joint. You can see it here. And the next step, we'll just move on to the joint D, free body diagram of joint D. Resolve it, sigma fx equation or Fy equation and fx, and just put it on the figure. Okay, towards the compression, I mean towards the joint compression, away from the joint it is positive tension. And a free body diagram of joint here I've taken here. Okay, I've taken this joint. Okay, this is 0.5 and this is a unknown member force. We are assuming it as a tension. Okay, so resolve it. Okay, Fy and Fx. So FAC is compression, FA is tension, and just draw it on the, I mean show it on the figure. Okay, AC is compression and AE is tension, and the joint C, draw the free body diagram. Okay, find the force FCE. Okay, so resolve it, and you can see here FC is nothing but tension, okay, away from the joint. So we have calculated this member forces in all the members of a truss, given truss. Now, with the help of the strain energy stored due to axial loading, that is W square L by 2AE, this W is nothing but the axial forces in all the members. That is W here plus W, that is W square L by AE. A is nothing but area, it is already given for all inclined members 1000 square mm, and for all horizontal it is 800 millimeter square. And W, for example, for this case, 0.577 P whole square into this length 4 meter divided by 2. Area is nothing but the inclined 1000 into E, Young's modulus is given. Like that, we have to sum it up for all the members, okay, for all the members. You can see 1, 2, 3, 4. All the 4 are having same magnitude, same length, same area. Just I have multiplied by 4 here. And this one is the horizontal. These two are having same magnitude, same length, same area. Multiply by 2. And this is having different magnitude, so I have shown separately here. Okay, so this is the total strain energy stored here, 0.0039 P square by E. And according to Castiglione's theorem 2, the partial derivative of the total strain energy with respect to the load, applied load, gives you the deflection at the point of application of the load in the direction of the load. So you can get this as your deflection 0.0078 P by E. You can substitute the E value here if you want to get the final answer. Thank you.